Hello everyone, I am Richard Burton and I am going to be giving you a quick rundown of chapter 13, which is the first chapter that we're going to be going into for hand tools. And I know if you're like me, you probably do not want to sit down and read an entire chapter just to try to get the understanding of what's in it. So I was going to try to do a rundown and kind of hit the high points of the chapter, and also show you what some of the items that are being mentioned in the chapter are, and also to kind of give you a little bit of important information about it at the same time. I'm coming from my home, where I have a small workshop, and inside this area is where I'm going to be doing my videos from. So if you hear cars go down the street or birds singing from the trees nearby, just try to block that out and know that these are times that none of us are used to doing, and we're just having to try to make the best out of what we've got. So with that being said, we're going to go ahead and be looking at page 185 in the Hand Tools textbook, and this is chapter 13. And the first item that it talks about is a vise. So most of us that's been in any kind of workshop or been in a school type of setting where you did maybe auto repair or metal shop or home ec or anything, did woodworking or something, you're probably familiar with a table with a vise mounted on it. So this is my own personal vise that's mounted on top of my personal toolbox. I kind of made this setup so it would be portable, so I can kind of move it around when I'm working. And this is a pretty handy way to have your vise located somewhere where you don't always have to work in one location. So in the book it says that vices are designed to hold a workpiece in a rigid position and allow you to have your hands free so you can do whatever you need to do to the workpiece. Also, it talks about certain vices are made where they are fixed, which means that when they're bolted in position, that's the position you have to go with. And then other vices have what they call a swivel base. So most of us probably know what the word swivel means. And this particular vise here does have a swivel base. So when I loosen the bolts, if this was on a table that was really large that I couldn't turn around, then I would need the vise to be able to move while the table stayed stationary. Another vise that I have over here is one that mounts onto a machine table. And if you notice, this is a fixed vise. Once you mount it in place, that's the position it stays in all the time. It does have slots where you can move it back and forth, but if you needed to actually turn the vise, you've got to take it loose from the mounting and actually rotate it to another location and bolt it back down. So that would be considered a stationary vise. Another thing that you want to kind of take into a notice right here is this particular vise does have a small platform up here that's basically been embossed into the cast iron, and it looks like it would be a nice place for you to be able to lay something down and bang on it with a hammer. But the book wants to emphasize, and I would also say it's a good idea they do, that vices are not intended to be used as anvils. Anvils are really large, massive pieces of steel that have been basically forged and conditioned for that kind of hard blows, and they are designed to be able to withstand that. Blacksmiths use them to form hot metals over them. You see sheet metal people use them to form metal into certain unique shapes. They're used for a lot of different types of striking objects against. But the vise is not designed for that. So this little piece right here is only designed for doing light tapping, maybe with a hammer, maybe just laying something down on a flat spot so you can possibly bear down against the edge of it and maybe tap a pin into a shaft or something like that. But it's not designed for you to literally take something and bang on it with an extremely large hammer, because what it's going to do is it's going to crack this metal right here. Because if you notice, this metal is actually it's hollowed right here. It's actually got a insert in it, and that insert is where the screw for the vise goes in and out as you turn the handle and bring this forward and backwards. So that is not designed to take a lot of abusive blows with a hammer. Another thing that the book brings out is when you're not using a vise, how should you leave it? So in most cases, you always want to leave something in the safest way that you can. And being that you would not want to leave a vise opened up really wide, especially if it was on a table that could be out inside a walking lane somewhere where somebody could come by and, catch a part of their body on it as they walk by, especially if they didn't notice it. So the book says the best way to leave a vise, the safest, is to bring it all the way to closed, but not tight. So you don't want to torque it down and leave it tight. You want to leave it all the way to closed and then bring it back till it's slightly open. You could say either slightly open or slightly closed. Either way would be kind of the same wording, but you want to bring it all the way up as close as you can get it without being tight. And that would be the way to leave a vise on a table that's not being used. The next thing is going to talk about, because we are in metalworking, we're talking mainly about devices and tools that are used in metalworking. So the next thing is a hacksaw. Most of us are familiar with hacksaws. Probably if anyone has a home shop, they have a hacksaw, because there's not too many other ways to cut metal unless you've got some power tools that like abrasive cutoff wheel or a bandsaw or something like that you're going to be able to cut metal. So when you go back to the old manual way of doing it, a hacksaw will be the tool of choice. So this is a hacksaw that is considered a high tension hacksaw, because you can basically use a lever to increase the amount of tension that's pulled on this blade. The more tension you can get on a blade, the better the blade will hold up to cutting. Because the last thing you want to do is for this blade to get flimsy while you're trying to push it through a piece of metal you're trying to saw. Of course, the book talks about hacksaws are being mainly used for cutting metal. That's true. They are designed for cutting metal. Yes, you can cut other things with them if that's all you got, but metal would be the main choice for having a hacksaw. The other thing that it talks about is that the hacksaw is basically two parts. You've got the frame, which is what holds the blade, and then you have the blade itself. The blades are pretty easy to remove. You just loosen up whatever's holding tension on the blade. There's two holes on each end. You just take the blade off and exchange it. One important thing to keep in mind about hacksaw blades is they are flexible. They're very flexible. In fact, they're kind of like a spring in a way. If you flex them, you let them go, they come back. If you try to flex them too much, sometimes they will bend, but most of the time they will break. They've only got a certain amount of flexibility before they will snap. And the reason being is because most hacksaw blades have a certain amount of hardness in the steel that they're made from. And with that hardness, also it increases what they call the brittleness of the metal. That being said, the reason you want to make sure the blade is put in and stretched really tight is so there's no flexibility to allow for that brittleness to cause a hacksaw blade to break while you're trying to saw through it. If you were sawing with a hacksaw blade that was loose and the blade bent enough while you were pushing on it, it would probably bend enough to go past or beyond this point and it would snap the blade. So you probably are sitting there thinking, yeah, I've done that. I've snapped the blade in a hacksaw. This is what your run-of-the-mill, buy in any old store type hacksaw. Most of you probably more familiar with this style. So you got your frame, you got your blade. If you notice, the only way you can put tension on this blade is by this wing nut on the end. Most of the time you cannot give yourself enough tension on a good blade with just the strength in your fingertips on a wing nut. So a lot of times these do not hold up very well to sawing through a lot of metals many times over, put it that way. They'll probably saw through a couple things, but they won't do it over and over again. The blade will eventually probably break because it's not tensioned well enough. The one thing to keep in mind is when you install a blade, your teeth are pointing in a certain direction. If you notice on this blade right here, it's got an arrow. That arrow should be pointing away from the handle. That also means that the teeth are pointing away from the handle. So when you're sawing through something, you're going to be putting force away from your body. So you're going to be pushing away, which is the most natural and efficient way to saw something anyway. You're not going to put the blade on and drag it back through to cut something. That's not the most efficient way to do it. So if you put a piece of metal into a vise, you're going to set up to saw it. You're going to put it and you're going to push away from it. Another thing to notice for safety is if you look in the if you look at figure 13-4 right here, it shows a person actually doing some sawing on with a hacksaw, and as they're sawing, they've got this hand placed on the frame, not down here on the metal like some people would think it's supposed to be, because if you do that, what's happening? You're going to be in risk of putting your blade right into your hand if for some reason that blade jumps out of the groove where you're sawing. So if you keep your hand up here, you saw back and forth, there's no risk in your hand getting cut by the hacksaw blade. And also too, with your hand up here, it's going to help you cut straighter than if you just kind of one-handing it and the blade's running all over the place while you saw it. One more thing that the book wants to mention is that a hacksaw blade has something called the teeth are set on a hacksaw blade, which means that each tooth goes this way, that way, this way, that way, this way, that way, set all the way up the end of the blade. It's kind of hard to see in the video, but if you were looking at this blade from the angle I'm looking at it, you can see that each of these teeth are alternating side to side. The reason that they do that is so that as you're sawing with this blade, you're creating a wider groove than the back side of this blade. So this part of the blade is not dragging behind through the material and actually creating friction and getting hot. It's just basically there to support the rest of the teeth, and it just floats through the groove without touching it. So that's one thing. If you cut good and straight with a hacksaw, then you're not going to wear out all the paint on the back of your blade. That should be an indicator that you're sawing really straight when the blade's not getting all the paint rubbed off of it. Because as long as you keep the blade up straight when you're sawing, only the teeth are going to do the cutting. and the blade's not going to be rubbing back and forth on the metal. One more thing that in table 13.1 mentions is each blade has what they call a TPI, which is teeth per inch. So on every inch of this blade right here, it has 18 teeth. And the purpose of that is the amount of teeth have a lot to do with what types of materials that you're going to cut. If you've got a 14 TPI, then you would be cutting stuff such as cast iron and soft metals, brass and aluminum. If you go up from there, 18 to 24 to 32, the materials change to like thinner wall materials, things that you would have less likely a chance for the teeth to get caught in if you're sawing something really thin like sheet metal, for instance. So if you had more teeth per inch, you're gonna not have as large a gap between the teeth, so it would saw thinner metals easier. So that's just something to understand and know about what the information is on these blades here. This is also 18T, which means 18 teeth per inch. This one is a 24T, which means you've got more teeth per inch. So you could saw thinner material without it hanging up and grabbing on it. The next metalworking tool that it mentions is a file. Most of us are familiar with files, probably have used them numerous times. Whenever you need to remove some material off of something, the file is pretty much the go-to item for that, unless you have a belt sander or you've upgraded to a bench grinder or something like that. Then the power tools kick in, material gets removed a lot faster. But sometimes you remove material too fast and you go from having something too large, now you got it too small. So sometimes the file is the perfect in between, because you're not going to remove the material so fast that you accidentally make it undersized. So it kind of gives you that balance. So files are also cutting tools that are made out of hardened metal, and to not go too much into that and take a lot of time, in order for a metal to cut another metal, it has to be harder than that metal. So if you're familiar with blacksmithing, then you've also probably have seen some blacksmiths. They take the hot metal out of the fire and they immediately put it into, it looks like either water or oil of some sort, and they quench the metal really fast. What they're doing at that point in time is they're heat treating the metal, making it hard. If you heat metal up and you let it cool slowly, the metal's not going to have as much hardness as if you cool it fast. So when you take a particular metal, like the metal that the file is made out of, and you take it into a heat treat process, then you make this metal a lot harder than most normal metals, which will allow this to be able to shave and cut material off of other metals very easily. So if you take a file and you put it against something that, like for instance, another metal that's as hard as a file, you're going to notice that the file doesn't do any damage to it. That's going to tell you that metal is too hard for you to file it. So you'll have to come up with another means for cutting that metal, which would be like a grinding rock or something, some other kind of material that's harder than just hardened metal, in which rock is made out of like hard minerals. So of course that's harder than metal. Okay, so it talks a little bit about the edge of a file. If you take a flat file like I have here in my hand, if you notice it's got an edge, it's got cutting edges on this side, and also on the small sides. The small sides also account for the file where you can cut shapes, and those shapes could be such as a slot or a notch, or maybe cutting a little square corner on something. Doing stuff like that with the edges is totally permissible to do that. One thing that it warns you about files, sometimes when you buy a file, it does not come with a handle installed. These particular ones did come with handles already installed in them. But sometimes when you buy files in bulk, they just come like this, with a round file with a sharp pointed tang. And then you buy the handle individually and you install it into this. Well, sometimes these two become separated and all you can do is find a file on hand and you're thinking, well, I've got the file, I need to file something, I don't know where a handle's at, so I'm just gonna go with it like it is. Well, it tells you never use a file without a handle because this is blunt and it's pointed and it could easily get stabbed into your palm. If you're sitting there filing on something and then all of a sudden you hit something solid and all that inertia goes back into the file and then your hand's buried into it, so then it stabs in. So keep that in mind. Always try to be safe and always conduct yourself as if anything that you're messing with could potentially hurt you, and do not risk getting hurt with a file like that. The next thing it talks about is with each file you have a type of cut with that file. The book says that you have what they call a single cut file. Single cut means that you only have one row of cutting edges. And then from those single cuts, you have what they call a bastard cut, which is a very coarse cut. Then you have a second cut, and then you have a smooth cut. So depending on how much material you're wanting to remove, how fast you're wanting to remove that material is gonna play into what type of cut file you need. If you're wanting to leave a very smooth finish, you would not want to grab a bastard file and try to get that, because there's no way you're going to do that, because it's going to be digging trenches out of the material and not taking smooth, flat, nice cuts when you're filing it. Another thing they make is called a double cut, which means that where you have single grooves on one, you have double grooves on another, which means you've got twice as the amount of cutting edges on that file. And from a double cut, you also have a bastard cut, which is a coarse cutting file. And then you have a single cut and a smooth cut, a second cut and a smooth cut with that also. And basically what that just means is you have more cutting edges, so you should be able to remove more material with less effort with a double cut file. And that's all just on preference of the types of files that you can basically purchase or that you have on hand. It says single cut files used for smoothing and finishing are usually called mill files. So usually a very smooth file can also be called a mill file, because it basically takes the finish down as if you were milling it with a milling tool. So it would leave you a nice clean finish at the end. Another point that the book makes is that all the files are heat treated, like I spoke about earlier, except for after they're heat treated, they anneal the tang right here, which means the tang can be bent without snapping off. If you try to bend this file, because it's been heat treated, it's back to what I said about the hacksaw blade. When you heat treat metal to a certain hardness, you make it brittle. Even though it's hard enough to cut metal, it's also very easy to snap if you try to bend it beyond its flexibility capacity. So if I took a file like this thick piece of metal and tried to pry up on a lid of a crate, more than likely I would break the file, because once I put some flex on this file, it's going to just snap. So files are not good for being used as pry bars, and you should probably know that's definitely not the correct use for them anyway. But it just wanted you to be aware that the tang can be manipulated. You can bend the tang up a little bit if you wanted to possibly make the handle be at an angle to what you were filing on for whatever reason, for clearance or whatever. You can bend that tang out of position without it breaking off. All right, so The other thing to just kind of notice about a files is files come in various shapes. This one's a triangle. This one is a square. This one is round. This one is flat on one side and half circle on the other. And then of course this one is all flat. The reason they come in different shapes is so you can mimic that shape into whatever you're filing. So you need to cut a V groove into something. You can file long enough with this file to get that V shape to basically pattern into the metal that you're filing it on. Say you need to cut a square slot in something. You can eventually file this down and get some nice 90-degree corners and continue to file down however wide you need the slot to be. Or if you need it square, if this is the right size square you need it to be, then that will make a square slot. So files can do a lot of various shaping on materials. So that's another reason if you're filing something that happens to be round in shape on the inside, like inside a hole, you're gonna need a round file to be able to smooth around a round hole like that. So a lot of uses coming into play with files, where you may not have machines to be able to do that. A lot of modifications on equipment have to be made, and of course you can't bring the whole piece of machinery into a machine shop to do it, and sometimes you can't remove the parts easily enough to take them into a shop. So you can get a file and bring it to the part on the machine and do the modification right there in place. Okay. Next thing that it talks about as far as metalworking tools is a tap. And the best way I can describe a tap is that it's a cutting tool that makes threads into holes. And these holes have to be pre-sized so the tap can thread into it, but also cut into the material. And as it's cutting into the material, it's going to leave a thread-like cut into the hole, just like the nut on a bolt. So if you take this nut right here, it's got threads inside of it that this is the same size tap, or the correct size tap for this nut right here. So if I forced it enough with the coating that's on the nut, I could get this to thread up on here. A lot of times with cutting tools, they're sharp, so they tend to want to start to cut into the coatings, and it makes it a little hard to thread it up on there just by hand. So taps are often sold in sets, and those sets include a tapered tap, which means it's tapered on the end so it's easy to start. Then you have a plug tap, which has a slight amount of taper on it, not as much as a tapered tap. And then you have what they call a bottom tap, which means that if you're taking this tap down into a hole that did not go all the way through the material, and you need to leave the threads as deep as possible, but you're going to have a bottom to the hole, then you need a tap that has very little taper on the end. So as you run this down into the hole, it's going to leave threads down all the way to the base of where the hole was drilled. So if you think about how often would you see tapped holes in something, well, if you happen to work on a car and you think about the engine block itself, how many items is bolted to the engine block? Well, all of those holes are probably blind holes, which means they have a bottom to them, and then bolts run into those blind holes. Well, those holes have to be tapped deep enough with threads so the bolt will go all the way as deep as it needs to hold the part onto the engine block. So that's one place where you'll see a lot of what they call blind holes, which is holes that a bottom tap had to be used to get the threads deep enough. So tap sizes come in all of your standard sizes for your bolts. If anybody's ever been to a hardware store and looked on the aisle where they sell fasteners, bolts come in many different sizes, standard inch size and metric size. So for every bolt size that's made, there is a tap out there that you can buy to create that thread in whatever you want to create the thread into. Like I said before, you have to make sure that before you put the tap in the hole, you have a pre-selected size hole that's got to be drilled in. If you look on page 193, there is a chart that shows you the tap drill sizes needed. So for every size tap, you have to use a certain size drill to make the hole. And that will leave you enough stock allowance in there for the threads to be cut into the hole without actually going too deep into the tap, causing it to basically bind up and get lodged in the hole. And because the tap's only going to cut down as deep as the threads of the tap can go. Another thing to keep in mind is this particular tap here is a 3/8/16, which means that the diameter of this tap should be somewhere close, very close to the size 3/8 of an inch, because that is what the outside of these threads should measure up to. That's how you determine the size of a tap. Another thing that it says in the book uses the illustration of a 1/4-20 tap, which means that it would be a 1/4 inch diameter tap. And the 20 represents how many threads per inch. So 20 would be you have 20 threads for an inch worth of running distance of the bolt. This is a 3/8/16 tap, which is a pretty standard tap, and this tap has 16 threads per inch. And one quick way you can verify that this is a 3/8/16 bolt is to take the tap and nest it into the threads of the bolt. And if they lay inside of it perfectly and match right into the cut, if you can see that, that tells you you've got the correct tap for the correct bolt. You can already tell it's about the same size, but in order to make sure you got the right pitch, these threads should mesh up perfectly, almost like a gear would mesh up with the right gear. Okay. So one thing it talks about when using taps is you've got to have some way to turn the tap. If you notice, these taps have already been notched with squares on top for you to be able to place them into some kind of wrench. So this is a tap handle that has a square jaw pattern in it that I can place the tap into it and tighten it down, and of course it's going to hold the tap in place. This is one type of tap handle. Another type is a bar type tap handle where you basically put the tap in and you just tighten down the bolt and it holds the tap in place. If for some reason you were using a tap and you didn't have this type of handle or this type of handle, you can find the right size wrench that'll fit over it and you can still turn this. And even in some cases, if you're in a very tight location, these type handles here are going to be too big to be able to get in there anyway, so you're going to have to do this with a wrench anyway. So you can also use a open end wrench to turn a tap if you need to. One other thing to keep in mind with taps is you never want to use a cutting tool on a piece of metal without the proper lubrication. And there is different kinds of cutting fluids for all different kinds of materials. And if you look on page 194, there's tapping lubricants chart that tells you a lot of different types of metals and all the different types of cutting fluids that would be specifically designed for those metals, which means that the cutting efficiency of the tap would be a lot better than if you used possibly the wrong cutting fluid with the wrong material. A lot of cutting fluids try to be general purpose, so they can handle pretty much every kind of metal that's out there, so you don't have to try to have a lot of certain ones. But if you get into a lot of exotic metals, and say you're doing production and you're tapping holes in those metals, you probably want to get a specified cutting fluid for that metal, so the tap's going to do the very best that it can. The more cutting fluid you use on a tap, the longer and sharper the tap will stay, and it'll last, and you won't have to replace them so often. There is one little trick that's mentioned in the book just under the table 13-3, where it says if you're tapping blind holes, which means the holes I talked about that did not have a bottom in them, holes that's been drilled into, solid chunks of metal like an engine block that didn't break through to the other side. One problem you have with taps is as you're tapping, you're cutting those chips away for the threads. Some of those chips can get broke loose and fall down into the bottom of the hole. So if enough of those chips fall into the bottom of the hole, they're gonna basically prevent you from being able to get down to the very bottom where you need to get your threads cut to. So you can use a mixture of oil and white lead on the tap to help keep the cuttings stuck to the tap while you're cutting it, so that when you pull the tap out, all the cuttings remain on the tap and do not fall down into the bottom of the hole. So that's just a little trick that was mentioned in the book that I wanted to bring out to you. Next, we talked about the internal threads of cutting into a nut. Now we're going to talk about cutting external threads, which is the threads like you find on a bolt. So this particular cutting tool is called a die. And a die, basically, as long as you got the right diameter stock here, say this did not have threads on it already, I could start the die on it and begin to turn it with cutting oil basically all over this part. And I could cut threads all the way down as long as I wanted to with this die until I felt like I had enough threads on it to do what I needed it to do. And then I would just bring it back off. Of course, it's going to make a lot of mess over here with cuttings as I twist this around, but you can do that to just about any kind of material that's the correct diameter for the threads you're needing it to be. And dies also come in a variety. This one happens to be a hexagonal type, basically the same shape as a nut. And then you've got rounded dies like this one here that have to have a special tool to put the round in, or else it's going to be hard to hold something round in shape. It's got a notch into the side of it that a set screw locks down. That also does the same size here. So I could run that in there as well. It's 3/8 too. It's like I'm starting at the wrong side, but it doesn't really. This one's a little bit tighter in cut than this one here, but they are both 3/8/16. Which brings me to the next thing about thread classes. You've got different classes of threads, which means these types of threads right here to the threads that are cut into to the nut itself. So you've got a class 1, which is considered a very loose fit. So if I run this on here and move it back and forth, it's kind of loose. This probably could be either class 1 or class 2, because it's basically just a regular old hardware store nut. It's nothing specialized about it. And then you've got a class 2, which is a medium tight fit. And then you've got a class 3, which is considered a very tight fit, which means that while I was putting this nut on here, it would probably have a lot of friction behind it. It would be very tight to even turn onto the threads by hand. And then you have what they call a class 4, which is a specialized, extremely close fit, which would be like nuts and bolts used on like aircraft, where you definitely don't want any of those vibrating loose during a flight. And so when you get into what they call aircraft grade bolts, it changes a lot of the specifications on those. Okay, the next thing it talks about is a cutting tool called a reamer. So what is a reamer? So a reamer, unlike a drill bit, has a lot of cutting edges. If you look at this on the video, this thing looks like it's almost perfectly shaped round. And there's a reason for that. A reamer is designed to come in behind a pre-drilled hole and create that hole to a smooth and perfectly round shape. A lot of times we think of drills as being like when we punch a hole in a drill, like this right here. You know, we drill that in and it goes in the hole and it leaves us a perfectly round hole. It looks to be perfectly round. But actually, if you try to put something round in shape inside that hole, a lot of times you find that the hole is not quite so perfectly round. So what we would do is, if we needed this whole 1/2 inch hole here to be perfectly round, we would use a drill bit just a size smaller, like this size here, to drill the hole. And then we would come back with a reamer and we would ream that hole until we got it to a perfect 1/2 inch size, which means we would basically shave out a small amount of material until we got that material removed to the perfect size of a 1/2 inch. Then we could come in with something that's exactly perfectly round and it would fit in there super tight. And like a line-up pin, for instance, or say you were trying to fit a shaft in a bushing, or not a bushing, but like a brass bearing material, or you could be putting it in a bushing that's going to go over something else. But any of those, you need the fit to be extremely smooth and you need it to be really close fitting tight. So a drill would not achieve that. So one thing to keep in mind when you use a reamer, because you're only taking out a small amount of material, that you never run a reamer in the reverse direction. A reamer cuts in what we typically consider forward direction in a drill press or a milling machine, which means that if you're looking down at the cutter is turning in a clockwise direction. So as you go down into the hole to ream it, you remain in a clockwise direction the whole entire time as you go in and as you come back out. In most cases, when you drill something, you do the same thing. You drill it going forward in, and then once you drill through the hole, you just pull it out. We typically don't forward and reverse any other tool except for a tap, because we're threading it in and then we're threading it out. So we have to go clockwise in, counterclockwise out for right-handed threads. And one reason you would not want to reverse a reamer is because you're wanting the hole to be extremely smooth, and if you reverse it, you're going to pull back the shavings that have already went back into these little slots here, the relief cuts, and you're going to pull that material back in over the top of the cutting edges, and it's not going to be cutting, it's just going to be rubbing all that material back into your finish. So it's going to be scratching the finish up and making a really nasty finish as you bring it back out. So forward, always with a reamer in rotation. And that pretty much concludes all of the metalworking tools for this chapter. I hope you got something valuable out of this information. And as we continue to move forward with other chapters, I'm going to do some more videos so you can at least see what's going on, and you'll be able to relate this once we get into the labs and we start using these tools for real, and you start making some of these parts in the lab projects. So goodbye for now.